Hello, Physics 11s. In this video, we'll talk about vectors. We'll talk about what vectors are and how we'll use them and how to add and subtract vectors. Okay, first of all, reminder, the difference between a scalar and a vector. Scalars are things that have magnitude or size only. Examples of those are time, length, and mass. Vectors, on the other hand, have both magnitude and direction. Examples are force, displacement, velocity. Here is an example of a force that is pulling in a certain direction. We're going to use the northeast, southwest quite a bit, and 30 degrees north of east just means, hey, start in the eastward direction and go 30 degrees north of that. So how I would show this vector is 40 newtons, and it is 30 degrees north of this coordinate direction of east. Okay, so vector terminology, we have magnitude, which is the size, the tail, and the head. Just to show you those, because when we add vectors, we do it in a couple of different ways, which we'll get to in a minute. Okay, different ways that we will use vectors in Physics 11. We'll talk about pulling a sled. We're a kid on a sled at an angle. We'll talk about launching projectiles at an angle and how we'll break those vectors into their different parts. Riverboat problems, where we have a boat that's trying to go across a river that is flowing, in this case, to the south. That current speed will be represented by a vector. We talk about resultant velocity is what we'll talk about when we're adding vectors here shortly. Okay, last example here is just things on ramps. We'll talk about, hey, it's gravity that makes things accelerate down ramps. So if we have gravity, we'll talk about how to break that gravity vector into its different parts. Okay, just some vector math, some trig review, just to show you this, which is also on your formula sheet. We're going to use both trig ratios for right triangles and also Pythagorean theorem quite extensively. Okay, when we add vectors, we talk about the resultant as the sum of vectors. We have two methods that we are going to use to add vectors. One is graphically, or the tip to tail method. The other is using components in the x and y direction. So here's an example of the tip to tail or graphical method. When we are adding vectors, we have to think about just moving this vector A to a certain spot and then adding vector B to it where we're adding the tip and the tail. This C is our resultant. Resultant in this case would be this C vector. Resultant is always drawn from wherever you started your first vector all the way to wherever you ended your final vector. Okay, here's an example. If we have a vector, or sorry, 8 meters pointing to the east, and then adding another vector to it, which has a magnitude of 5. If we're looking at what this answer would be, or the resultant, I would think of drawing a vector that starts at the first vector, ends at the last vector. I'm going to just call this, or show again, this is the resultant. In this case, our resultant would be 13 meters, and we always have to include a direction. In this case, our direction is also pointed to the east. If we end up with an example where our vectors are in different directions, like 12 meters to the west, so I'm going to show this graphically. 12 meters pointing to the west, which is in our case to the left, plus 5 meters to the north. I'm going to put my second vector where we are going head to tail, and then the resultant in this case would be a vector that goes from the start all the way to the finish. I'm going to call it R for resultant, and then after this point, we're just going to go and do some math. Okay, so this R resultant is going to be pointing in a certain direction, so I'm going to label theta in that triangle. I'm first going to use Pythagorean theorem to find the length or the magnitude of my vector. So this is R squared is equal to A squared plus B squared. Okay, and then we can plug and chug some numbers here. That means that R squared is 169, and then R, if we take the square root of both sides, the length or the magnitude of this thing is going to be 13 meters. Okay, solving for the angle, if we have theta shown where we do, this side across from theta is going to be opposite Our 12-meter side is going to be adjacent. So we'll use tangent theta, which is opposite over adjacent. In our case, that's just 5 over 12, or the tangent theta is equal to 0.416 repeated. Okay, then to find theta, we have to do the inverse tangent of both sides, and we'll end up finding what that angle theta is. And in this case, angle is 23 degrees. Please make sure to plug and chug that on your calculator, make sure that we're getting the same values. And then to state your final answer, we have to state our resultant with both a magnitude and also a direction. Okay, direction's a little tricky because we have to say, okay, well, 23 degrees, well, I'm going to use my northeast, south, west. I'm going to need to reference one of those four coordinate directions when referencing this 23 degrees. So I'm going to use the westward direction. I'm going to say, hey, my angle, it has to be 23 degrees in the north direction of west. So we'd say 23 degrees north of west. Okay, then I put a box around this. So it's done. We'll move on to the next one. Okay. Oh, an example that you can use to check your work. So FET vectors. If you just go and Google FET vectors, you will get taken to an applet that looks like so. So this is an applet where you can put vectors on here and move them around. I've already added one vector that is 12 meters, or it has a magnitude of 12. It is pointing to the west direction. On this screen, that tells me theta is 180 degrees. The way that direction is measured from in this app and in many mathematical applications is 0 degrees is your positive x-axis. You can go up to the top right and click on this theta. It will show you, hey, there's 180 degrees, or in our case, pointing to the west. Okay, this 5, what I'm going to do is I'm going to arrange this vector B, tip to tail or head to tail with my vector A. I'm going to change the magnitude of it so it is 5 meters to the north. I'm going to go up and click on this sum, and then I'm going to move this so that it's drawn properly, and we can see that, hey, if that vector S is highlighted, our magnitude of this thing would be 13.0. Okay, and just to check the theta in this case is given as 157 degrees, so that's going to be the angle between the positive x-axis and this vector. And then if I add that extra 23 degrees that we just solved for, that makes sense because that total should be 180 degrees. Okay, so FET vectors is just an applet that you can use to check answers to your work as you go. Okay, when we are subtracting vectors, we are going to add the opposite. Here's an example. What that means is we are going to go and add the opposite. So if we have this negative, we're just going to change that vector around. So we're going to add the opposite, and all that means is that the direction is going to change. Okay, so if we have 8 meters to the east, you'll have to excuse my unstraight line. And then we add to it a vector that is heading 2 meters back to the west. Our resultant in this case will be a vector that goes from start to finish. That vector, we can see that's going to be 8 minus 2, or a magnitude of 6. And our direction is going to be to the east. Let's go back here. So this would be 6.0 meters in the east direction. Put a box around that, and we're done with it. Okay. Okay, let's try another one where we have 16 meters per second pointing to the west. There's my 16 meters per second pointing to the west. Minus 12 meters per second south. This is a vector subtraction, so I'm going to add the opposite. So 12 meters per second north. I'm going to add these things head to tail. Our resultant will look like this. I'm going to put theta in here. Okay, and then after this, we're just going to go and do some math. Okay, so same as before, we're going to use Pythagorean theorem. I'm going to call this R for my resultant. R squared is going to be equal to 12 squared plus 16 squared. Okay, you can work that through and you get down to R squared is equal to 400. Square root of both sides. We know that the size or the magnitude of this thing is 20. Okay, finding theta, the tangent of our angle theta is going to be the opposite divided by the adjacent. In our case, that is 12 over 16, or the tangent of theta is equal to 0.75. Okay, to find theta, we'll have to do the inverse tangent of both sides. And we find that our theta in this triangle is 37 degrees. Then when we go and state our answer, we'll state our resultant with a size, or 20 meters per second. It's going to have a direction that is 37 degrees. And that is, if I start from the west, from this west arm, I'm going to be going north of that. So that's north of west. Okay. Another way that you could state this direction is if we use this north line as our reference line. If we use this angle coming down this way, that angle in our case would be 53 degrees. Another way that we could state this direction for our vector would be 20 meters per second. It would be 53 degrees. In this case, it would be west of north. We start at north and we're going to the west of that. Either one of these directions are correct. Both of these answers are correct. You'll notice that 37 and 53, those two vectors, they are complementary. They add to 90 degrees. And the direction, the order that we state, north of west or west of north, those are just swapped. Okay, we'll try a couple more here. Here's one where we have 4 vectors. I'm going to look along here and find that, hey, we just have one vector that is subtraction. So I'm going to just go and change that around so it's an addition. Okay, the next thing I'm going to do here is I'm going to group together my north and south coordinates. If you look at this question, we have 1 meter north and then 3 meters south. If we add those together, 1 meter going north and then 3 meters going south, in the north-south direction, we're going to end up 2 meters south of where we started. Think of drawing that resultant in there. It would be a resultant that looks like so. Okay, so that's just for the north-south direction. Okay, then if we group together the east-west direction, we could say, okay, well, if we go 6 meters to the west and then another 2 meters to the west, our overall resultant in this case in the east-west direction would be 8 meters to the west. And I do that because it makes it a little easier for drawing our vector triangle where we just have to draw 2 vectors. Well, we went 2 meters to the south. We went 8 meters to the west. Our resultant will look like so. So I'm going to call this our theta up in here. Just move that 2 out of the way. Okay, after we get our triangle set up, now we're just going to, again, go and do some math. Okay, so r squared will be 2 squared plus 8 squared. R squared is 68, or r being 8.2. In our case, the tangent of theta is 8 over 2, or 4. Theta is going to be the inverse tangent of 4, or theta will be 76 degrees. Okay, so to state this answer, we'll have our vector that is 8.2 meters, where we have drawn our theta, that is 76 degrees. That is, we start at south and go over in this direction. We're going to be going 76 degrees west of south. Okay. If we wanted to reference the west direction, we'd say, okay, this has to be 14 degrees in here because 76 plus 14 is 90. So another way that we could write this direction is 14 degrees south of west. Box around this thing because we're done. And we'll move on to the next one. Okay, one last question here. In this case, if we go for a stroll taking the following route, 4.1 kilometers east, then we go 3.6 south, 2.6 east, and then 1.4 kilometers north, our resultant would look something like so. Okay, so again, for this question, I think it'll be easiest for us to group together our north-south and our east-west components. Oh, I almost skipped over distance. What distance did you walk? Distance is just adding up all of those numbers, showing where exactly, whoops, that's 2.6 plus 1.4, just saying how far we walked. So that distance works out to, hey, we went for an 11.7 kilometer walk. That's a good healthy walk. Okay, and then for displacement, we'll look at vectors in the north-south direction. On the north-south direction, we have 3.6 south and 1.4 north. So in the north-south direction, we're going to end up 2.2 kilometers south of where we started. In the east-west direction, we've gone, hey, 4.1 kilometers east and another 2.6 kilometers east. So our overall displacement in the east-west direction is 6.7 kilometers to the east. Okay, I'm going to short form this. If this is our starting point in our north-south direction, our vector triangle will be 2.2 kilometers to the south, 6.7 kilometers to the east. Okay, our resultant, we'll use this as our theta. Okay, now we'll go and do some math. I'm going to let you go and do this math. You should find that your resultant is 7.1 kilometers. If you go and solve for theta, we should get theta is equal to 72 degrees. Please go plug and chug, make sure you get those numbers. Stating this answer would be 7.1 kilometers. Direction would be 72 degrees east of south. Okay, put a box around this guy. This guy's done. Okay, that wraps it for today. If you could please go have a look at chapter 3, worksheet number 1. Try questions 1 to 6. Before next time, stay safe, stay healthy, and we'll see you again soon.